Hi everyone, welcome to part 3 of the Cosmology lecture. This is lecture 14. This part will be considerably shorter than the other two, I promise you. In this part, I want to talk about some of the more difficult to solve and also amazing cosmic mysteries. In part 2, we talked about the kinds of energy densities that can dominate the universe and how those energy densities affect the expansion of the universe. We talked about some of the slightly more mundane mysteries, I guess you could say, that are specifically the horizon problem, the flatness problem, and the magnetic monopole problem. We talked about cosmic inflation, which we think is the solution to those mysteries. And in this video, I want to talk about two of the big ticket item mysteries that you'll see in the media oftentimes, and also if you read about cosmology, you'll see these. And these are dark matter and dark energy. Let's start with the idea that over the past 20 years or so, we have discovered tons of evidence that we can really only account for about 5% of the energy density of the universe. Let's start with dark matter. Dark matter, we think, constitutes around 20 to 23% of the energy of the universe. And dark matter is some kind of matter, some kind of particle that has mass that we think surrounds and is inside galaxies. And we think that the vast majority of matter in any given galaxy is actually dark matter. The reason we think that this matter exists is for a couple of reasons. The main reason would be because the rotation of galaxies is not explainable via our current understanding of gravity, and also by just by just accounting for all the mass in the galaxy that you can see. If you take these two things together, you cannot explain the rotation of galaxies. Let's go to this slide where I want to talk about galactic rotation curves in a little bit more in detail. Here I have a galaxy at the top right. This is a fairly typical spiral galaxy. And let's assume that all the mass in this galaxy is visible to us. It's visible either in the form of stars or gas, etc. And let's also assume that the laws of gravity as we understand them are correct. What we can do is predict, by measuring the mass distribution in the galaxy, we can predict how fast some star, let's say this star here, should be traveling around the center of the galaxy. Remember, this is a spiral galaxy, so the stars in it will rotate around the center. And when we do so, we can then apply this concept to many stars in the galaxy. And each star has a distance r from the center. This distance r can change continuously. Therefore, you can look at stars that are very close, even farther, somewhere in the middle, etc. And you can plot these points, and you end up with what we call a galactic rotation curve. This is a plot of the velocity of a star around the center of the galaxy versus its distance from the center of the galaxy. And if you were to predict what this curve should look like, you would get curve A. This is what we expect to find when we study galactic rotation curves. Instead of just doing this theoretically by plugging numbers into equations, we can do this experimentally. We can actually determine how fast various stars are rotating around the center of a galaxy, and then we can plot those values on the same plot. We can create an experimental galactic rotation curve. And what we actually find is something very different than what we expect to find. Instead, we find curve B. What we find is that galactic rotation curves are flat. In reality, they are what we call flat, meaning that the velocity of stars near the center is roughly the same as the velocity of stars near the edge. And this is the opposite of what we expect to see. Well, opposite is a weird word to use. This is very different than what we expect to see. What we expect to see is this dashed blue curve, curve A, where the velocity of stars near the center is much greater than that near the edges. Therefore, one way of explaining this problem is by saying that the velocity of stars near the edges of spiral galaxies is way too large. These stars are traveling way too fast. And there are two explanations that might come to mind. One explanation might be, well, maybe our understanding of gravity is incorrect, because as I mentioned to you, we get curve A by taking our understanding of gravity and plugging in data from a given galaxy. We figure out what is the approximate mass distribution of the galaxy, where the mass is in the galaxy, and then we throw that into our equations. So you might think, well, our equations are incorrect. The second solution that comes to mind is maybe there's a lot more mass in this picture, in this galaxy, than you can see. Maybe there's a lot of mass which is invisible, that does not interact with light, and therefore you cannot observe it directly, but you can observe its gravitational effects. Now, you might be inclined to think that the second one is not a good explanation, and probably we should look at our equations and figure out if they're wrong. That's a very reasonable thing to think. The problem is that no one has come up with any way of altering our equations of gravity to explain this phenomenon, but also explain all of the other gravitational effects that we see. There are theories which attempt to do this. These are called MOND, Modified Newtonian Dynamics, MOND theories. And people work on these, but as I mentioned, they've not been very successful because you cannot just modify gravity to explain galactic rotation curves that are flat. You have to explain all the gravitational phenomena that we see. That includes cosmological phenomena. So no MOND model has ever really been able to do that. In addition, there's direct evidence for the existence of a particle that has mass that's invisible. And that is, I don't believe I have a slide for it, but that is what we call the bullet cluster. I'm sorry that I don't have a slide for this, but I'm going to explain to you what the bullet cluster is in words, and I'll try to draw it as well. So this is evidence for the second explanation, the one which says that maybe there's tons of mass that you can't see in each galaxy, and that is causing the stars near the edges of the galaxy to rotate way too fast. And the direct evidence for this is what we call the bullet cluster. And maybe I'll post the picture of this on Blackboard right next to the link for this video, since I'm not going to be able to do a good job drawing this. In fact, that's what I'll do. I won't try to draw it. But in any case, the bullet cluster is two galaxies that are colliding. And there are two ways to determine where the mass is in this cluster, in this mess of a collision. One is to look at the visible matter. So you use various techniques to figure out where the mass is by observing electromagnetic radiation. Another way to determine where the mass is to use gravitational lensing. Remember that space can act like a lens because energy and matter curve space. So if you have a very dense bundle of matter in some compact massive object in some region of space, it will very severely curve space, and that space can act like a lens. Well, by measuring the gravitational lensing effects around this, what we call the bullet cluster, we can then extrapolate where the mass is, because mass the presence of mass itself, the distribution of mass, causes this lensing effect. So you can go backwards and look at what the distribution of matter is. What you find is that where the matter is according to gravitational lensing is very different than where it is by just looking for it. And that implies that there's tons of mass in regions around this bullet cluster that you can't see. And by the way, this mass actually is in the right place to be dark matter, because we believe dark matter has certain properties, such as, for example, it doesn't interact with regular matter very often or at all, and it doesn't interact with itself. It doesn't form atoms and stars and etc., because it interacts with itself only very weakly. All right, I'm going off on a tangent here, but this is the evidence for what we call dark matter. And dark matter, we believe, constitutes the vast majority of matter in the universe. Not the vast majority of energy, but the majority of matter. And this constitutes about 22-23% of the energy of the universe. Before you continue, I want you to watch this video on dark matter. And also this video from PBS Spacetime. I want you to watch these two videos, and when you're done watching them, please come back to this point in the lecture. Let's now talk about dark energy. I talked about dark energy a little bit earlier. We think that dark energy exists. We come up with this concept in the first place because we observe that the universe is accelerating in its expansion. This is very strange because there's no known form of matter or energy which can cause the universe to accelerate outward. And hence we refer to it as dark energy. Now, dark energy must have certain properties. So we do know some very basic things about dark energy, but very little. I want to go through the history just a little bit. In 1998, a team of 48 astronomers discovered that the universe is accelerating. They did this through observing supernovae in different galaxies. In a previous part of this lecture, I mentioned to you that a basic interpretation of dark energy is that it exists as this constant form of energy which permeates the entire universe. And as the universe expands, the density of this energy remains constant. This is one basic interpretation. I want to mention to you that this has somewhat of a theoretical basis. You might ask, is there any area of physics, any theory or model or whatever that would predict a background energy, this kind of constant energy throughout the universe? And actually there is. Our best model of particle physics, our model that explains the behavior of little particles, is called quantum field theory. And quantum field theory predicts a background energy. The problem is that quantum field theory predicts a background energy which is about 10 to the 120 times larger than what we actually observe. Dark energy must be very dilute. Even though most of the energy of the universe is in dark energy, the universe is a big place. So actually it's very dilute. The density is very small. And quantum field theory predicts a density of this energy which is 10 to the 120 power too large. So 1 with 120 zeros. I'm not going to write them all out. And this has been referred to as the worst prediction in the history of science. When I was a graduate student, a very well-known speaker who works on this problem and other problems, came to speak to us. And he explained this problem to us, and he stated this is the worst prediction, not only in the history of science, but probably in the history of human civilization. It's very difficult to be this wrong. But this is a good thing, because this means that there are mysteries to be discovered. We want to be wrong, since that means that we have stuff to learn, stuff to discover. I want you to watch now this video here on dark energy. Alex Filipenko is one of the people who discovered the accelerated expansion of the universe. He's an excellent speaker. I had the pleasure to watch him speak when I was a graduate student. Actually, this is not the same person who told us about this worst prediction in the history of science. That's someone different. But I also got to see Alex Filippenko speak, which was really great. So I encourage you, not encourage you, I'm mandating you to watch this video. I don't think you'll regret it. Okay. Now that you've watched this video on dark energy by Alex Filippenko, I want us to talk about the fate of the universe. We don't know the fate of the universe, but we can make some speculations. I like this poem by Robert Frost. I don't think was talking about the fate of the universe, but we can reinterpret his words because it sounds like he's talking about it. So what would be the fate of the universe? Will it be fire or ice or something else? Well, we don't know, but if dark energy abates by some mechanism, the universe could collapse. This doesn't seem very likely, but we don't know what dark energy is, so it's possible it will disappear one day or morph into something else. And this by itself wouldn't necessarily cause a big crunch, but it's possible that changes in the composition of the energy density of the universe could give rise to the universe collapsing instead of expanding. And this would be referred to as a big crunch. If dark energy fails to abate, if it just continues or gets if the effects get more severe, then the universe will continue to expand forever, and this is known as the big freeze. Because as the universe expands forever, it will just become very cold. Remember, as the universe expands, it cools. Eventually, all nuclear fusion would cease because there wouldn't be enough fuel, so to speak, for nuclear fusion. We wouldn't have stars. We would just have dilute gas and black holes, and then eventually all of the gas presumably would fall into black holes. This is related to what we call the heat death of the universe. Actually, this doesn't refer to a hot universe. It refers to a universe in which you cannot have regions where there would be enough thermal energy for life. And the universe in this scenario would consist really of just very cool matter, maybe eventually falling into black holes. These black holes would eventually radiate away. So eventually, over extremely long periods of time, we wouldn't even have black holes. We would just have a background radiation. They would just radiate photons, and that would be all we would have. But this universe wouldn't allow for local regions to have enough thermal energy to support life, at least as far as we know. Okay, that's a really morbid topic, but in any case, this scenario that I mentioned, this heat death, is not going to occur if it occurs for many, many billions of years. There's also a term called the Big Rip, which refers to a universe that is accelerating out of control. If dark energy increases over time greatly, let's say, then the universe could accelerate to the point where we have a big rip. I want to talk about the age of the universe. I've mentioned what this age is without going into too much detail, but we can use our models of cosmology, the Big Bang Theory, which means we're using general relativity and thermodynamics to compute the age of the universe, and we get about 13.8 billion years. There are some people who will say, by the way, that the Hubble time gives you the approximate age of the universe, which is 1 over... well, anyway, I don't want to go into it, but whenever you see the Hubble time or the Hubble radius, for example, these are just approximations. So this video is already too long. But in any case, I just want to mention to you that we measure the age of the universe more approximately than just the Hubble time or Hubble radius. Okay, that's it. The rest of these lecture slides consist of questions that we unfortunately don't have time to go over. But thank you for watching part 3 of the cosmology lecture, lecture 14, and I will talk to you in another video.